Welcome back to the deep dive. Today, we are really getting into the nuts and bolts. We're dissecting the digital nervous system, the thing that underlies basically every modern business, every app you use, every single transaction. We're plunging deep into the foundational components of information technology.
Yeah, the building blocks.
Exactly. Because look, the digital world isn't magic, right? It's actually a brilliant, highly structured integration of the physical stuff and, well, the logical stuff. So our mission today is to kind of move past just the basic definitions. We want you to get a really clear, structured view of how hardware and software actually integrate to create genuine, strategic business value.
Okay, let's unpack this. Maybe we can start right away by defining that critical relationship between these two pillars.
Absolutely. That relationship, it's really the foundation of this whole deep dive, isn't it? Every single robust information system, it relies on these two intrinsically linked halves.
Two sides of the same coin. Precisely. On one side, you've got hardware.
Oh.
Now, this covers all the tangible things, the physical components you can actually touch. We're talking input devices, output devices, storage, the processing parts themselves. And crucially, hardware is the essential platform. It gives you the capacity, the speed, the sheer physical presence needed to run operations.
Okay, the foundation. And then the other side provides the brains.
That's software.
Right.
Software is the intangible bit, the instructions, the compiled code, the logic, the algorithms, basically everything that directs the hardware to perform specific tasks. Think of it like this. You could have the most powerful multi-core processor, but it's really just an expensive paperweight without an operating system and applications telling what to do.
Right.
So software is that operational blueprint. It's what makes the hardware actually useful.
That analogy really works, doesn't it? Hardware is the, let's say, reliable, scalable body. And software is the constantly evolving, intelligent brain. They're completely codependent. Hardware does nothing without instructions.
It's inert, yeah.
And software can't run without the hardware's, capacity to execute it.
And understanding that tight coupling immediately highlights the four key roles hardware plays, always. Doesn't matter if it's a supercomputer or like your local ATM.
Okay, what are those?
Well, first, input, capturing the raw data. And this could be pretty complex. It's not just someone typing. It could be automated sensor data from a factory floor or maybe high-speed data feeds from a financial market.
Got it. Raw data in.
Second, processing. This is where the CPU, the central processing unit, and the system memory get to work. They transform that raw data into meaningful, usable information, calculations, manipulation, logic.
That data into something useful.
Third, storage. You need to preserve that process data, right? Make sure it's accessible, persistent, secure for later use for analysis.
Okay.
And finally, fourth, output. Presenting the results. Could be to users visually, could be physically like a printout, or even audibly, or maybe to other systems.
So designing a system isn't just about picking the fastest processor then. It's about making sure that whole four-part data lifecycle, input, process, store, output, flows smoothly without bottlenecks.
Exactly.
And the key strategic insight here, I think, is that the performance, the reliability, and maybe most importantly, the scalability of your hardware choices that directly impacts the long-term success of the entire system.
Precisely. Because if your hardware is the bottleneck, let's say you have slow storage holding back a really fast CPU. Well, you haven't just wasted money on the CPU. You've actually built a point of failure into your system.
Right.
So designing systems requires really matching that hardware capacity to the workload you expect it to handle. Efficiently, cost-effectively, right from the start.
Okay, so now we understand the core requirements. Let's explore the massive diversity of physical hardware out there. The days when IT just meant, that beige box under your desk.
Yeah.
Those are long gone. Hardware has become incredibly specialized.
It really has. We can sort of categorize the hardware ecosystem based on its intended purpose and its scale.
Let's start where most of us interact with it daily. Personal computing. These are the general purpose machines, right? PCs, laptops.
The workforces, yeah.
They're designed to balance processing power, storage, portability. You see them everywhere. Offices, schools, home entertainment. They're flexible tools running all sorts of different applications. Then moving to what's probably in your pocket right now, mobile devices, smartphones, tablets. What defines these?
Extreme portability, obviously. Constant connectivity. And they really rely on touch interfaces, advanced cameras, lots of sensors, accelerometers, GPS, that kind of thing. Their whole architecture is optimized for battery life and running apps.
Makes sense. Okay, let's swing to the other end of the spectrum. The heavy lifters providing the backbone for entire organizations.
Right, that's where you find centralized power, servers and mainframes. Servers are basically powerful computers built for network tasks, data storage, hosting applications. They often run 247 in a dedicated data center.
And mainframes, you don't hear about them as much now.
Less common, true, but they still offer unmatched reliability and massive transaction processing power. Think big banks, governments, systems handling billions of real-time transactions. They're critical for certain legacy systems.
Okay. And then there's the category that's everywhere, but we almost don't notice it.
Ah, yes. Specialized and embedded systems. This is the sort of invisible tech integrated directly into other machinery. It's in modern cars, industrial control systems, smart appliances like your fridge maybe, sophisticated medical equipment.
ATMs you mentioned earlier.
ATMs, exactly. They perform a very specific task, often something mission critical, using specialized chips and usually quite minimalist operating systems.
All right, shifting gears a bit. We've got all this hardware. How do we interact with it? How do we get data in? Let's maybe skip the super basics of keyboards and mice and focus on how input is evolving strategically.
Good idea, because we've definitely moved beyond just simple typing. I mean, sure, the standard QWERTY keyboard and the multi-touch touchpad on laptops are still essential. But modern input is much more about direct interaction and high specialization.
Like touchscreens. They seem like a perfect example of integrating input and display.
They are. Kiosks, smartphones, point-of-sale systems.
Yeah.
They allow for a much more intuitive, direct way to manipulate content. You're touching what you see.
And then you mentioned specialized tools.
Yeah, controllers. These are precision instruments tailored for specific tasks. Think about high-sensitivity joysticks for complex surgical robots.
Wow, okay.
Or gamepads, but used for really immersive training simulations. Or even industrial barcode scanners that capture inventory data with incredible accuracy.
And they often give feedback, right?
Exactly. Many provide crucial haptic feedback vibrations, resistance. That makes the physical sensation part of the data flow. It can enhance speed and drastically reduce user error, especially in high-stakes environments like surgery or complex manufacturing.
But the real game changer, you hinted at it, is the move towards automated input, where the machine itself is the input device.
Indeed. This is the world of IoT, the Internet of Things and industrial sensors. You configure these devices once, and then they just continuously collect data. Temperature, pressure, movement, security metrics, whatever they're designed for. Minimal, sometimes zero human interaction needed after setup.
And that's critical for things like smart factories.
Critical for industrial automation, infrastructure monitoring, smart cities, you name it. The insight here, strategically for businesses, is huge. Automated input doesn't just streamline things. It creates data streams that were literally impossible to capture manually before.
So better data.
Dramatically better. More accurate, much more granular, and collected much faster, often in real time. This gives you operational awareness that can lead to things like predictive maintenance fixing a machine before it breaks, or real-time adjustments to supply chains based on live data.
Okay, so we've got this massive flood of data coming in, maybe automatically, it gets processed. Now we need intelligent ways to get the results out. And that brings us to output devices.
Right, and the obvious starting point is visual feedback monitors.
But beyond just size and resolution, what matters today?
Well, features like high refresh rates are crucial for certain things. Smooth motion in design work or gaming. Technologies like OLED offer incredible contrast, perfect blacks, superior color accuracy. That's essential for professional photo or video editing.
And strategically?
Strategically, just the simple ability to use multiple high-resolution monitors can drastically boost productivity. Think about data analysts, software developers. More screen real estate means less time switching windows, more information visible at once.
Makes sense. What about physical output?
We still need printers, of course. From high-volume laser printers churning out shipping labels and logistics,
Right.
to specialized photo-quality inkjets or those versatile multifunction devices that scan, copy, maybe even fax. And don't forget audio output speakers, headphones. They provide essential alerts, immersive sound for training or entertainment, clear voice communication for collaboration.
But the output world is really being redefined, isn't it? By a couple of cutting-edge technologies that kind of shift the whole paradigm. You're thinking virtual reality, VR, and 3D printing.
Exactly. VR is way beyond just gaming now. It uses specialized headsets, motion sensors to fully immerse users in digital 3D environments.
And businesses are actually using this.
Absolutely. We're seeing major corporate investment in VR for things like high-risk training simulations. Imagine training someone on complex machinery or emergency procedures without any actual physical danger.
That's powerful.
It is. Also for product design, iterating on virtual prototypes, and even sophisticated remote collaboration, walking through a virtual model together. It lets organizations train and prototype much faster, cheaper, and safer.
And the other one, 3D printing. That's output creating actual physical objects.
Right, also known as additive manufacturing. It takes a digital model and builds it, layer by painstaking layer, into a tangible object. And it can use a surprising range of materials, plastics, resins, even metals.
The strategic potential seems enormous.
It's revolutionary. Rapid prototyping, turning a design concept into a physical model in hours or days, not weeks or months. Creating customized medical devices, like perfectly fitted prosthetics, or making highly specialized on-demand replacement parts for complex machinery right where they're needed. It's effectively decentralizing manufacturing capability.
Okay, so from input, processing, output.
Right.
That brings us to making sure the data sticks around. Permanence, storage, and connectivity. The data has to live somewhere reliable.
And we still face that strategic storage dual capacity versus speed. On one side, you have HDDs, traditional hard disk drives.
Spinning disks.
The spinning magnetic disks, yeah. They still reign supreme for sheer capacity and low cost per gigabyte.
Yeah.
That makes them the go-to for bulk storage, long-term backups, archiving data. You don't need instantly what we sometimes call cold data.
But the drawback.
Speed. Access speeds are significantly slower because of those moving mechanical parts. They can easily become I/O bottlenecks in systems that need fast data access.
Which is why we have SSD solid-state drives. They seem to be the standard now for anything active.
They really are. They use flash memory, no moving parts at all. This means blazing fast read and write speeds. Applications launch almost instantly. Computers boot up dramatically faster.
They're more expensive, though.
Per gigabyte, yes, the cost is higher. But they're also more durable because there are no moving parts to break. And the performance boost they provide gives such a significant return on investment in terms of productivity and user experience that they're pretty much mandatory for any active workload today. The operating system, applications, frequently accessed data.
So in big systems, it's about using both.
Often, yes. That's called tiered storage. You use high-speed SSD arrays flash storage for your active databases, the stuff you need now, and then you back that up or store less critical data on massive, more cost-effective HDD arrays for archival purposes.
And storage isn't just inside the machine anymore, is it? We need to talk about storage beyond the box, like external drives.
Right. Portable drives, usually connecting via USB 3.0 or maybe Thunderbolt for higher speed. They're ideal for local backups, transferring large files between machines, or situations where you need absolute control over the data and maybe offline access. Security is a factor, too. You can physically lock it away.
But the big strategic piece of modern storage is undoubtedly the cloud.
Oh, absolutely. Cloud storage providers like Amazon S3, Google Cloud Storage, Azure Blob Storage uses vast remote data centers accessed over the internet. It offers unparalleled convenience, what we call elastic scalability. You can grow or shrink your storage on demand, and robust remote access from anywhere.
What are the key operational benefits there?
Several. Automatic syncing across multiple devices is huge. Robust versioning, meaning you can easily roll back to previous versions of a file if something gets corrupted or accidentally deleted. Integrated collaborating tools are often built in, essential for teams spread across different locations.
And reliability.
That's a big one. Cloud providers handle the complexities of data replication and redundancy behind the scenes. They typically offer very high levels of durability. The statistical likelihood of not losing your data that would be incredibly expensive, maybe prohibitively so, for most organizations to build and manage themselves locally.
Okay, so the data's captured, maybe processed, definitely stored safely. Now we need to really dig into the engine that makes the decisions, the central processing unit. CPU. This is the command center, right? The actual brain of the system.
It really is. The tireless command center. Its core function is, well, monumental. It fetches instructions from memory, decodes them, executes them.
Does the math.
Does the math, the logic, coordinates all the input-output operations, manages the flow of data between different parts of the system. It's orchestrating everything.
And internally, how does it work? What are the key parts?
Its architecture is incredibly refined for speed. We can break it down into, say, three main functional areas. You've got the control unit, CU, that's like the conductor of the orchestra. It directs the flow of data between memory, the ALU, and the input-output devices.
Okay.
Then there's the arithmetic logic unit, ALU. This is where the actual calculations happen, the addition, subtraction, multiplication, division, and also the logical comparisons, like, is this value greater than that value? The heavy lifting.
That's surrounding these. You mentioned speed is critical.
Exactly. Critically, surrounding the CU and ALU are the registers and cache. These are small pockets of extremely fast memory located physically very close to or even right on the processor core itself.
Why is that closeness important?
Because accessing data from the main system RAM, even though RAM is fast, still involves a delay as the data travels across the motherboard. Registers and cache provide near instantaneous access to data the CPU is currently working on or likely to need next. This prevents the CPU from sitting idle, waiting for data.
Got it. So when we look at CPU performance, we often hear about clock speed in gigahertz. Is that the whole story?
Not really, no. It's an important metric, but incomplete. Clock speed tells you how many cycles the processor runs per second. But another key factor is instructions per cycle, IPC. How much useful work gets done in each cycle. Some CPUs are just more efficient than others at the same clock speed.
And cores. We always hear about multi-core processors.
That's probably the biggest factor today. Having multiple cores allows the CPU to execute multiple instruction streams simultaneously in parallel. This is crucial for multitasking, running many applications at once, and for applications specifically designed to use multiple threads, like video encoding or complex simulations. It dramatically increases overall throughput.
And the cache you mentioned. Size matters there.
Absolutely. That ultra-fast cache size is vital. CPU cache is usually tiered L1, L2, L3, with L1 being the smallest and fastest right next to the core. Larger amounts of cache, managed intelligently by the processor, significantly reduce the time spent waiting for data from slower memory latency.
Yeah.
This keeps the CPU cores fed and busy, maximizing efficiency.
Okay, so if the CPU is the decision maker, the brain, then RAM is like its short-term workspace, its whiteboard.
That's a great analogy. RAM, random access memory, is high-speed, temporary, or volatile storage for all the programs and data that are currently active. When you open a dozen browser tabs, load a big spreadsheet, start a game, all that working data lives in RAM.
And volatile means?
Power off, data gone. It's temporary. But its speed is why it's strategically essential. The CPU can access data stored in RAM many, many times faster than it can from even the fastest SSD.
So more RAM is generally better.
Definitely. Having a large amount of fast RAM is crucial for smooth multitasking. It allows you to run many things at once without the system slowing down to a crawl. It's also vital for virtualization, running multiple operating systems, and for memory-hungry applications like CAD software or video editing suites. Honestly, insufficient RAM is probably the single most common cause of perceived system slowdowns for everyday users.
Right. And beyond RAM, there's a whole memory architecture supporting the CPU.
Yes, it's a hierarchy based on speed and cost. At the top, you have the tiered cache built right into the CPU, fastest, smallest, most expensive per bit. Then comes the main system RAM. Below that, there's virtual memory. This isn't actually physical memory. It's a technique where the operating system uses a portion of the hard drive, or SSD, as a sort of overflow space when the physical RAM fills up.
Does that work well?
It works, in the sense that it prevents the system from crashing immediately. But accessing data from the hard drive is so much slower than RAM that performance takes a massive hit. You'll notice the system becoming very sluggish.
Okay. And what about memory that doesn't forget when the power goes off?
That's ROM, read-only memory, or more commonly now, flash memory. This holds essential, non-volatile firmware like the system BIOS or UEFI. That's the basic software needed to start the computer up, initialize the hardware, and load the main operating system from the storage drive.
Gotcha. So all these sophisticated components, CPU, RAM, cache, they need a physical home and ways to talk to each other. That's the motherboard's job.
Precisely. The motherboard is the main circuit board. You can think of it as the central nervous system or the circulatory system of the machine. It physically houses the CPU socket, the RAM slots, expansion slots, and connectors for storage drives and peripherals.
And it provides the pathways.
Yes, it provides the essential power delivery pathways and the physical communication structure. That communication happens over buses. These are high-speed communication channels like PCIe, Peripheral Component Interconnect Express, used for graphics cards and fast SSDs or USB for external devices. The speed of these buses dictates how quickly data can move between different components.
And something called chipsets manage this flow.
Correct. Chipsets are a set of specialized integrated circuits on the motherboard that manage the data flow between the CPU, main memory, and the peripheral buses. They essentially act as traffic controllers. The chipset determines many of the motherboard's capabilities, what type and speed of RAM it supports, how many PCI lanes it offers, the number and type of USB ports, and ultimately, the compatibility and upgrade options available for that specific platform.
Okay, this detailed look at the system architecture brings us to something you touched on, a trend that's really accelerating and redefining processing power: specialized processing and acceleration.
Right. We've kind of hit practical physical limits on how much faster we can make single cores and general-purpose CPUs run due to heat and power constraints. So the big gains now are coming from specialization.
And the prime example is the graphics processing unit, GPU.
Absolutely.
Yeah.
GPUs were originally designed for one specific, highly parallel task, rendering the millions of pixels needed for 3D graphics and games and visualizations. They have thousands of small, efficient cores optimized for doing similar calculations simultaneously.
But now they're used for more than just graphics.
Oh, much more. That parallel processing power turned out to be incredibly useful for other tasks. This led to GPGPU general-purpose computing on GPUs. Now, GPUs are indispensable for high-performance computing. They offload massive parallel workloads, things like scientific simulations, financial modeling, processing huge data sets, and critically training artificial intelligence models. This frees up the main CPU to manage the overall process and handle tasks that require faster single-core speed.
And here's where it gets really interesting, right? Moving beyond GPUs to chips designed specifically for AI.
Exactly. This is where the specialization gets intense. We have TPUs, tensor processing units, developed initially by Google, but now others are making similar chips. These are ASICs, application-specific integrated circuits optimized purely for the types of matrix multiplication heavily used in machine learning workloads, especially deep learning. They dramatically speed up both training AI models and running them, inference.
And NPUs.
NPUs, neural processing units, are similar but often smaller, lower-power chips integrated directly into mobile devices like smartphones or other client hardware like laptops. They handle AI tasks locally. On the device itself, think real-time language translation, advanced photo processing, facial recognition, or smart battery management without needing to constantly send data back and forth to the cloud.
So TPUs for the big data center tasks, NPUs for the edge devices. What else?
In areas needing extreme speed or highly customized logic, you find ASICs designed for other specific tasks, and FPGAs, field programmable gate arrays. ASICs are custom designed for one job and are incredibly fast and efficient at it. Think high-speed network routing equipment or chips designed solely for cryptocurrency mining. FPGAs are interesting because they can be reprogrammed after manufacturing to perform different hardware-level tasks, offering a balance between the performance of an ASIC and the flexibility of software. They're used in areas like high-frequency financial trading or prototyping new chip designs.
The strategic value here seems clear. Specialized chips just blow general-purpose CPUs out of the water for specific tasks.
For those specific, highly parallel or specialized tasks, absolutely. They offer orders of magnitude better performance or power efficiency. This provides a significant competitive edge and enables applications, particularly in AI and large-scale simulation, that simply wouldn't be feasible or cost-effective using only general-purpose CPUs. So if we pull all this hardware knowledge together, the challenge for designing or choosing a system becomes clear. The key performance factors aren't about optimizing just one component in isolation.
Yeah, it's the whole package.
It's the synergistic balance. You need to consider CPU speed and the number of cores, the amount and speed of RAM. The type of storage SSDs are basically essential for active data. Now, sufficient GPU power if you have graphics or AI workloads, and the speed of the interconnecting buses.
And you mentioned things we often overlook.
Yes. You can have the fastest components in the world, but the system can't sustain peak performance without adequate cooling. High-performance parts generate a lot of heat, and you need a stable, sufficient power supply to feed everything reliably. Skimping on cooling or power is a recipe for instability, throttling, or even hardware failure.
So the core idea is matching the hardware profile to the actual business workload.
Precisely. That's the essence of smart system design and procurement. Don't overspend on components you don't need, but don't create bottlenecks by underspecifying critical parts.
And this focus on optimization, on specialization, it's setting the stage for some really futuristic trends in hardware, isn't it?
Definitely. The future seems to be defined by two big forces: continued specialization and also decentralization. We're seeing a huge surge in AI-optimized hardware, more MPUs, more specialized accelerators being built into everything. The goal is often to move AI processing away from the centralized cloud, closer to where the data is generated.
Which leads to edge computing.
Exactly. Edge computing is the trend of shifting processing power physically closer to the data source. Think smart sensors on a factory floor, analyzing data locally, IoT gateways processing information before sending summaries to the cloud, autonomous vehicles making real-time decisions. This reduces latency, the delay in getting a response, which is critical for applications needing immediate action, like industrial automation or remote surgery. It also reduces the amount of raw data needing to be sent over networks.
Okay, and then there's the really far out frontier, quantum computing. Still mostly experimental.
Very much so, but the potential is staggering. Quantum computers don't use traditional bits, zeros and ones. They use qubits, which can exist in multiple states at once, thanks to quantum mechanics. This allows them to tackle certain types of problems, particularly in optimization, materials science simulation, drug discovery, and breaking current forms of encryption that are simply intractable for even the most powerful classical supercomputers today. It's still years away from widespread practical use, but the potential breakthroughs are game-changing.
Okay, we've built the body, the physical hardware platform. Now we need to install the brain, the intelligence. We need software. This is the essential instruction set that makes the hardware actually do something useful and drives business processes. And we generally categorize software into two main camps, right? System software versus application software.
That's the fundamental split. System software is the often invisible but absolutely critical layer. Its job is to manage and operate the computer hardware itself. It provides the platform for everything else to run on.
So the operating system is the main part of this.
The operating system, OS, like Windows, Mac OS, Linux, Android, iOS, is the core component, yes. It handles fundamental tasks, managing memory allocation, scheduling which tasks get CPU time, controlling input and output devices. But system software also includes things like device drivers, small pieces of code that let the OS talk to specific hardware components like printers or graphics cards, and utility programs for tasks like disk formatting or system diagnostics.
It's like the operational bridge between the hardware and the apps we actually use.
Exactly. It ensures that when an application needs a resource, say, it wants to save a file or perform a calculation, the system software handles allocating the necessary CPU time, memory space, and storage access efficiently and securely. Without robust system software, the hardware just sits there.
Okay, so if system software runs the machine, application software is what we, the users, interact with to get things done.
Correct. Application software focuses directly on user tasks and, crucially, translating specific business needs into digital tools. This is the software you use daily. Your word processor, your spreadsheet, your company's accounting system, your inventory tracking software, your web browser, your communication tools like Slack or Teams.
And how businesses get this application software varies a lot too, doesn't it?
It does. There's packaged software, the off-the-shelf solutions you buy or subscribe to. Think Microsoft Office, Adobe Creative Cloud, commercial accounting packages like QuickBooks. They're designed for a broad audience.
Versus building it yourself.
Right. Custom software is tailor-made, developed specifically for an organization's unique processes or requirements. This is often much more expensive and takes longer to develop, but it can provide a perfect fit and potentially a competitive advantage if the process itself is unique.
And the third major category, which seems dominant now,
is software as a service, SaaS. These are applications hosted in the cloud by the vendor, and you access them typically through a web browser or a dedicated app, paying a recurring subscription fee. Examples are everywhere. Salesforce for CRM, Google Workspace, Microsoft 365, countless specialized industry tools.
So the advantages are things like immediate updates, scalability, access from anywhere.
Exactly. And it shifts the cost model for businesses away from large upfront capital expenditures, CapEx, for buying licenses towards ongoing operational expenditures, OpEx for subscriptions.
When a business is choosing between these models, package, custom, SaaS, the decision point seems really complex. It's not just about the price tag, is it?
Not at all. The key concept here, strategically, is total cost of ownership. TCO is the strategic hammer, really. You have to look beyond the initial license fee or the monthly subscription cost. The savvy organization considers all the other costs involved over the software's entire lifecycle.
Like what?
Well, potential hardware upgrades needed to run the new software effectively. The costs of implementation and integration, especially getting it to work with your existing systems, this can sometimes dwarf the initial software cost. The expense and effort of migrating data from old systems to the new one.
And ongoing costs.
Huge ongoing costs. Staff training is a big one, and also retraining when you have staff turnover. Then there's ongoing support and maintenance, which might be included in SaaS, but is an extra cost for packaged or custom software. And critically, you have to consider the multi-year pain and cost of vendor lock-in if the software becomes deeply embedded and is very difficult or expensive to switch away from later.
So ignoring TCO can lead to major budget blowouts and operational headaches down the line.
Absolutely. It's a classic mistake. You need to think long-term. Now, moving up to the enterprise level, the big goal is often system integration. This leads us to enterprise-level systems, primarily ERP and CRM.
Right, these massive systems designed to connect everything. Why is that integration the goal?
Because historically, different departments, finance, HR, manufacturing, sales, often had their own separate systems that didn't talk to each other. This creates information silos, inefficiency, inconsistencies. Enterprise systems aim to tear down those silos.
Up and provide.
They aim to integrate all the core business processes, finance, human resources, supply chain management, manufacturing, sales, customer service, into a single unified system. The ultimate strategic goal is to achieve a single source of truth for all critical organizational data. Everyone works in the same up-to-date information.
Okay, let's break down the two main types. ERP first.
ERP, Enterprise Resource Planning Systems, primarily focus on unifying the back-office operations. They manage complex, cross-functional processes. Think financial accounting, procurement, buying stuff, manufacturing resource planning, inventory management, human resources management. Market leaders here are companies like SAP and Oracle.
They sound incredibly complex to implement.
They are notoriously complex.
Right.
Implementation projects can take years and cost millions. Customizing the modules to fit specific business needs often leads to conflicts. And establishing strong data governance, ensuring data is accurate, consistent, and secure across all those integrated functions is extremely challenging, but absolutely vital for success.
Okay, so ERP handles the back office, CRM handles the front office.
Generally, yes. CRM, Customer Relationship Management Systems, focus on managing all interactions with customers. They track customer data, manage sales pipelines and opportunities, monitor marketing campaign effectiveness, handle customer service requests and history. The goal is to get a complete 360-degree view of the customer.
And the insight they provide helps.
It's crucial for understanding the entire customer journey, identifying sales opportunities, improving customer retention through better service, and targeting marketing efforts more effectively. Salesforce is probably the best-known CRM provider, but there are many others. So what does this all mean for the business at the end of the day? Having these integrated ERP and CRM systems allows for truly coordinated operations.
Give me an example.
Okay, imagine manufacturing knows exactly what the sales team has promised a customer and when. Finance can track the real-time cost of inventory being used in production. HR knows the skills needed for upcoming projects scheduled in the ERP. This level of coordination allows the organization to make faster, more confident decisions, operate more efficiently, and ultimately achieve better overall business outcomes.
Okay, coordinating operations is one thing, but making better strategic decisions based on all the data being collected, that's a different challenge. That's where business intelligence, BI, and analytics come in.
Exactly. BI and analytics are all about the sophisticated transformation of raw data, often vast amounts of it, coming from ERP, CRM, websites, sensors, wherever, into actionable insights.
Actionable being the key word.
Absolutely. The purpose is to provide the evidence needed for better, faster, more informed strategic decision-making. It supports things like predictive forecasting, what's likely to happen next, and it helps with competitive analysis. How are we doing compared to others?
What kind of tools and capabilities are we talking about here? It's more than just spreadsheets, I assume.
Oh, much more. Key capabilities include highly interactive data visualization tools that make complex data understandable through charts and graphs. Real-time dashboards that track key performance indicators, KPIs at a glance. Increasingly important are self-service reporting environments, which empower business users and managers to explore data and create their own reports without needing constant help from IT specialists.
And more advanced stuff.
Yes, this is paired with advanced techniques like predictive analytics, using statistical models to forecast future outcomes. AI models are being used more and more to detect subtle trends, patterns, or anomalies in data that humans might miss. Think detecting potential fraud or predicting customer churn.
What are some common tools people might know?
Tools like Microsoft Power BI, Tableau, ClickSense, or specialized platforms from SAP or Oracle are widely used. They essentially transform vast data lakes or data warehouses into decision-making factories.
And the strategic impact. How does this really help a business?
The impact is profound when done right. BI directly improves operational efficiency by highlighting bottlenecks or areas of waste. It helps mitigate risk by detecting potential problems early, like compliance failures or security threats. And critically, it ensures that the operational data being collected actually aligns with and supports the organization's overarching strategic goals. You can see if your actions are actually moving the needle on what matters most. Finally, in this software section, let's look at the strategic choices around acquisition and emerging platforms. How do companies get this software, and what's coming next?
Okay.
The fundamental dilemma often starts with build versus buy. Should we develop custom software internally or buy a pre-built package or subscription?
When does building make sense?
Building custom software is typically justified only if the internal process the software will support is genuinely unique and provides a significant competitive advantage. If everyone else does payroll the standard way, there's little value in building a custom payroll system. But if you have a unique manufacturing process or a proprietary analytical model, building might be necessary. The downsides are high cost, long development time, and the ongoing burden of maintaining it yourself.
So buying is usually the default.
For standard business processes, yes. Buying packaged software or subscribing to SaaS is generally faster to implement, has a lower initial cost, though TCO is still key, and leverages the specialized expertise and ongoing development resources of the vendor.
Okay, build versus buy. What about the philosophy behind the software itself? Open source versus proprietary?
This is another major strategic choice. Open source software like the Linux operating system or the Apache web server has its source code publicly available. Anyone can use it, modify it, and distribute it, usually under specific license terms.
The advantage.
Often, lower upfront cost, though support might cost extra. Tremendous flexibility because you can modify the code, and often a large active community providing support and developing extensions.
And the risks?
Support can be less predictable than a commercial contract. Ensuring security and timely patching might rely more on the community or internal expertise. For mission-critical systems, some organizations prefer the guarantees that come with proprietary software.
Which is?
Proprietary software is owned and controlled by a specific vendor. You typically pay for licenses or subscriptions. The source code is kept secret. The advantage is usually professional vendor support backed by service-level agreements, SLAs, consistent updates and patching cycles, and often perceives stronger security controls and accountability from the vendor. The main downside is the cost and the potential for vendor lock-in.
All right. Looking ahead now, what are the emerging trends in software platforms?
The emphasis is definitely on speed, flexibility, and ubiquity. Mobile and cross-platform development is critical. Users expect a consistent experience whether they're on a laptop, tablet, or smartphone. Supporting the Bring Your Own Device (BYOD) trend in workplaces means applications need to run securely on various operating systems.
And platforms to speed up development itself.
Yes, we're seeing a huge rise in emerging platforms designed for acceleration. Low-code, no-code development tools like Microsoft Power Apps, Salesforce Platform, or OutSystems are empowering citizen developers. These are often business users with deep process knowledge but limited traditional coding skills, allowing them to build and deploy functional applications much more rapidly, using visual interfaces and pre-built components.
That sounds potentially disruptive.
It is. Alongside this, there's a continued shift towards cloud-native architectures. Building applications using microservices, containers like Docker, and serverless functions like AWS Lambda or Azure Functions. These architectures are designed for the cloud from the ground up, offering incredible scalability, resilience, and efficiency. The overall goal is to deliver better applications faster, more securely, and make them accessible everywhere via the internet. #TagV, software management, security, and lifecycle.
Okay, so we've acquired the software, maybe built it, maybe subscribed to it, it's deployed. But the work doesn't stop there, does it? Effective management is crucial, starting with something maybe not glamorous, but vital: licensing and compliance.
Absolutely vital, and an area where many companies, frankly, fall short and expose themselves to significant risk. Software licensing defines the legal terms under which you're allowed to use the software.
And there are different types.
Many types. You have single user or per-seat licenses, which typically tie the right to use the software to one specific physical device or one named individual user. Then there are enterprise or volume licenses, negotiated for large organizations, allowing installation across many computers, often with tiered pricing based on quantity.
And open source licenses.
Open source licenses vary, but common ones like GPL or MIT allow free use and modification, but often come with conditions regarding how you distribute any modified versions.
Yeah.
And of course, the now ubiquitous subscription SaaS model, where you pay periodically, monthly, annually, for ongoing access to the software and associated services. You never actually own the core software intellectual property in this model. Think Microsoft 365 versus buying an old perpetual Office license.
Why is tracking all this so critical? Compliance.
Compliance is absolutely critical. Misusing software licenses, like installing more copies than you've paid for, can lead to hefty fines during vendor audits, legal action, and significant reputational damage.
So companies need a system for this.
Yes, robust software asset management. SAM tools and processes are essential. They will accurately track what software is installed where, reconcile that against the licenses owned, and prevent overuse. Furthermore, especially when relying on SaaS vendors or cloud providers, you have to rigorously vet their compliance. Do they meet data privacy requirements like GDPR if you handle European customer data, or IPO for U.S. health information? Because ultimately, your organization is responsible for protecting that data, even if it's physically stored on a vendor's server.
That responsibility is huge.
Okay,
This ongoing management effort ties directly into maintaining the system, lifecycle management. Software isn't static, it evolves.
exactly. Software systems are like living things. They need continuous care throughout their lifespan. This starts with planned upgrades. These are major releases that introduce significant new features, change the user interface, or represent a major architectural shift, think in migrating from Windows 10 to Windows 11, or moving to a completely new version of an ERP suite.
And upgrades require effort.
Significant effort. They demand extensive testing and development or staging environment first. User training is usually required. And they often need significant budget allocation for the software itself and the implementation effort.
And then there are the smaller updates.
Yes, patches. These are smaller, much more frequent updates released by vendors to fix specific bugs or, most critically, to address security vulnerabilities that have been discovered.
How important is patching?
It is arguably the single most important routine security practice. Applying security patches promptly, as soon as they are released and tested, is absolutely crucial. Failure to patch known vulnerabilities is consistently the leading cause of successful cyber attacks and data breaches. It's leaving the door unlocked when you know someone has the key.
So the whole software lifecycle involves.
It involves the initial acquisition, the careful deployment, the ongoing support, including patching and upgrades, and eventually the planned retirement or replacement, decommissioning of the software when it's no longer fit for purpose or supported by the vendor. Planning for that retirement phase is often overlooked, leading to companies running old, unsupported, insecure software, what we call technical debt, which is incredibly risky.
And one practical detail about keeping things current.
A crucial detail, often impacting users directly, is that applying patches or major upgrades to critical systems frequently requires scheduled system downtime. This is a planned period when users cannot access the system while the updates are installed, configured, and tested before making the system leave again. This needs careful planning and communication.
That continuous need for patching links directly to the broader topic of security and implementation. Protecting these systems is a constant battle.
It truly is. Protecting systems from sophisticated and persistent cyber threats requires a layered defense strategy, often called defense in depth. You can't rely on just one tool.
What kinds of tools are essential?
You need a suite of tools. Network firewalls at the perimeter, and often internal firewalls segmenting the network. Dedicated antivirus and anti-malware solutions on all servers and endpoints, laptops, desktops. Data encryption is critical both at rest, when stored on disk like using BitLocker in Windows, and in transit when moving across networks. Modern endpoint protection platforms, EPP, or endpoint detection and response, EDR systems, like Microsoft Defender for Endpoint or CrowdStrike Falcon, provide advanced threat detection and response capabilities right on the user devices.
But tools aren't enough, right? Practices matter.
Tools are only half the equation. Effective risk practices are paramount. This includes mandating multi-factor authentication, MFA, wherever possible, especially for accessing sensitive systems or data. MFA means even if a threat actor steals a password, they likely can't log in without the second factor, like a code from an app or a security key. Enforcing strict role-based access control, RBAC, based on the principle of least privilege. Users should only have the minimum permissions absolutely necessary to perform their job functions, nothing more. Regular security auditing and log monitoring are essential to detect suspicious activity. And increasingly, organizations are adopting a zero-trust architecture mindset.
Zero trust.
Zero trust basically assumes that no user or device should be trusted by default, regardless of whether they are inside or outside the corporate network. Every single access request must be verified based on user identity, device health, location, and other contexts before granting access to resources. It's a major shift from the old trust but verify model.
So the ultimate goal of all this security software and these proactive practices is,
It's multifaceted. Minimize the organization's exposure to costly data breaches and ransomware attacks, maintain compliance with industry regulations and data privacy laws, and fundamentally protect the business's reputation, customer trust, and financial stability. A major breach can be devastating on all fronts.
okay, one last crucial piece. You can have the best, most secure software, perfectly managed, but none of it matters without successful implementation and adoption, right? People have
Yeah.
to actually use it effectively.
Exactly. A brilliant piece of software that sits on the shelf or that users actively avoid because it's too complex or poorly implemented is just a massive sunk cost.
So how do you ensure successful implementation?
It starts with meticulous project planning.
Mm-hmm.
Rigorous testing is non-negotiable, first in isolated test environments, then often with pilot groups of real users, beta testing or user acceptance testing, UAT, before a full rollout. And there needs to be tight coordination and communication between the IT team implementing the software and the business units who will actually use it to ensure their functional requirements are truly being met.
And getting users on board. Adoption.
User adoption is driven primarily by support and training. This means providing clear, mandatory, ideally hands-on training sessions tailored to different user roles, creating easy-to-access resources like quick reference guides, FAQs, or video tutorials, and having reliable, responsive help desk support available, especially during the initial transition period when questions and issues are most common.
And how do you know if it worked?
Crucially, success must be measured. You need to track usage metrics. Are people actually using the new system and its key features? Are you seeing the expected productivity gains or efficiency improvements, the return on investment ROI? And you need to gather constant feedback from users through surveys or direct conversations to identify pain points and opportunities to refine the software configuration, the processes around it, or the training methodology itself. It's an ongoing cycle. Hashtag Tangelia, synthesis and outro.
Wow. Okay, we have covered a lot of ground today. We've navigated this incredibly complex terrain, from the physical silicon of hardware to the intricate logic of software. If we were to recap the core insight, what would it be?
I think the core insight is the absolute interdependence. Hardware provides that essential foundation. It dictates the reliability, the scalability, the raw operational capacity. It sets the physical limits, speed, connectivity, mobility.
The body and the software.
Software is the crucial intellectual layer. It's the intelligence. It's what turns that raw compute power into actual viable business solutions. It drives productivity. It integrates all those disparate processes across the enterprise. And it enables the complex, data-driven decision-making that's absolutely required to compete today.
So the key takeaway for anyone listening.
The key takeaway is that neither exists effectively, let alone optimally, without the other. They are deeply intertwined. The most successful organizations, the ones really leveraging technology strategically, treat both hardware and software as core strategic assets.
Not just commodities off a shelf.
Exactly. They don't just buy them as commodities. They select them, they integrate them, they manage them intentionally, carefully, as specialized tools that need to be tailored to maximize specific organizational value and achieve specific business goals. And if we connect this to the bigger picture, look at the trends. The velocity of change we're seeing is really being driven by the ever tighter integration of these two forces.
How so?
Well, look at hardware. The future there is clearly about increasing specialization. Think TPUs, NPUs, specialized accelerators, and also aggressive decentralization through edge computing, pushing power out from the center.
Okay.
Simultaneously, the future of software is being defined by accessibility and speed. Think low-code, no-code platforms making development faster and available to more people. Think SaaS models delivering sophisticated capabilities instantly via subscription.
So it's hardware getting more specialized and closer to the data, while software gets easier and faster to deploy.
Precisely. And this strategic integration, this combination, is creating systems that are fundamentally faster, much smarter, and pushing the actual point of processing power and decision-making closer to the user, closer to the essential data source than ever before in history.
That acceleration, that combination of specialized hardware and agile software, it really raises a monumental question, doesn't it, for any company planning their next big technology investment or system architecture?
It really does. This raises, I think, a really important strategic question for listeners to ponder. As specialized hardware like those TPUs and MPUs we talked about increasingly dictates the peak performance potential for certain kinds of specialized software, particularly in areas like AI. How will businesses strategically balance the need for potentially custom-built software designed to perfectly match their unique competitive processes and leverage that specialized hardware to the max? Against the undeniable convenience, the standardization, the lower initial cost, and the perpetual update cycles offered by the subscription-based world of SaaS platforms. Where is that tipping point? When does the perfect but expensive and hard-to-maintain fit of custom code outweigh the agility, scalability, and predictability of the purchased platform, even if that platform can't fully exploit the underlying specialized hardware?
A critical balancing act, something definitely worth thinking about as you plan your next major technology roadmap or investment. That's all the time we have for this deep dive. Thank you so much for joining us.